Okay, we're at Unit 2 now. We're going to start Unit 2. This is Day 1A, Polynomial, Linear Functions, and Modeling. We've done some linear functions, we've done some modeling. Now we're going to talk about polynomials mixed in with it. Our learning target, to identify polynomials along with degree and leading coefficient, and to recognize and graph linear functions and use these functions to model situations and solve problems. So just a definition here. A whole lot going on here, but just kind of break it down for us. It says let n be a non-negative. Well, n is the powers, so all of these powers have to be non-negative. They have to be positive powers. So to be a polynomial, you can't have any negative exponents. So they're non-negative integers, which means they're whole numbers. Can't have any decimals in the exponent, can't have any fractions like that. And let a sub 0, which is the constant, a sub 1, a sub 2, all the way up to a sub n. So these are just all of the coefficients. All the coefficients of the terms have to be real numbers, and the first one cannot equal 0, because if it does, then that doesn't exist, because if that's a 0, 0 times anything is 0, and that term is gone. So that's the only reason they put that in there. So it is a polynomial function of degree n. So degree is the highest power you see, and then the leading coefficient is a sub n, which is the coefficient of the term that has the highest power, so the one with the degree. The 0 function, f of x equals 0, is a polynomial function. It has no degree and no leading coefficient, but it is a polynomial function. It's a flat line at 0. So polynomials are defined in continuous in all real numbers. So this is kind of something special about polynomials. It's a nice little characteristic of them. They are defined everywhere, so there's nowhere they're not defined, and they are continuous everywhere. So meaning the domain of all polynomials, if it meets this definition up here, the domain is going to be negative infinity to infinity, no matter what, because it's defined everywhere, so you can plug anything in. Because it's continuous in all real numbers, that means there's no points of discontinuity. So no points of discontinuity. So these are smooth curves, go up and down, and they go up to infinity or down to infinity, but they definitely go left and right to infinity forever. So using this definition up here, state whether these are polynomial functions. So maybe look through those, pause the video, and try those out, and label, maybe do yes, no, yes, no, yes, no, and then we'll talk about the degree and leading coefficient later. You can try it if you want, but so go ahead and pause the video now. Okay. Hopefully you pause the video. Hopefully it doesn't have time to pause the video. This first guy, it meets all the criteria. All of these numbers are real numbers. All of the exponents, and this one doesn't have an exponent, so it's just a constant. All of those exponents are non-negative integers. Again, you can just call whole numbers. So this one is a yes. This guy here, right there, you got a negative exponent. No, not allowed. It has to be non-negative. This guy here, the whole thing's being square rooted. So no, not a polynomial. Here, I do have real number, exponent, which that's a 1. Should have mentioned that's a 1 up there. And then this exponent, those are non-negative integers, so that's a yes. Okay, now the ones that I said yes to state the degree and the leading coefficient. So here on this one I said yes, the degree, the highest power I see is a 3. So the degree is 3, the leading coefficient, I'll spell LC, the leading coefficient is 4. Going down here, the highest power I see, and this one's kind of a trick question, they're trying to trick you. Normally, in standard form, the highest degree is first, then the next highest is second, and it goes in descending order. It kind of counts down. This is not standard form, but still a polynomial. So even though that 4 is over here, the degree is still 4. It means the leading coefficient is -2. Okay, down here, so we said we're going to model situations and solve problems. So that's what we're going to do down here in this guy. The Welcome Home Apartment Rental Company has 1,600 units available, of which 800 are currently being rented at $300 per month. A market survey indicates that for each $5 decrease, so if they lower their rent, more people would rent from them. So you'd get about 20 new leases for every $5 you drop the price, according to their survey. So first, determine a function, R of X, that models the total income realized, which just means how much money they got, how much income they get, where X is the number of $5 decreases in monthly rent. So just think that the total income, so R of X is going to be the total income. So that's the number of apartments times the rent per month. Okay, so the number of apartments right now, currently, is 800, but it says that for every $5 decrease, so we could add 20 new apartments. So for every $5 decrease, we'll add 20 more apartments. So that would tell me the number of apartments that I'm renting. And then the rent per month then, it's going to start out at 300, and you're going to take $5 away for every increment. So again, X is every $5 decrease. Okay, so X just represents every $5 decrease. So if I look at these guys here, and that's about it. I don't have to multiply that out. Okay, that's called factored form. If I want to put it in standard form, I have to multiply everything out, put the highest degree first, and go from there. But it didn't say I had to do that, so I'm not going to worry about it. Now it says find a graph for rent levels 175 to 300, which means that your X, so you'd have no decreases up to 25 decreases. That clearly shows the maximum. So I'm going to get my calculator and type that in. And so I got this here in the Y equals spot. And instead of just hitting graph, they got these special, this domain, it's a specific domain I want to look across. So I'm going to push window. I'm going to go from 0 to 25. Okay, now my Y values on this could be pretty high here. You could actually, let's say, maybe I'll just give it a guess. I haven't done this problem yet, so I'm not exactly sure. Let me just throw out a guess here, because the Y value is going to represent the income. It's going to be a lot of money. Okay, so let's put a whole bunch on there. Let's just say like $500,000. And I'm going to graph it and see what happens. That was a lucky guess. Now, if you want to kind of get an idea, you could push trace and see like it's floating around 250,000-ish. So I might change my window and change this to, let's say, 260,000, just so I can see everything here. So you see there's a definite peak here. There's a definite maximum right here. So I'm going to find my maximum. It clearly shows. So that's pretty much it. I just, that was part B, was making the graph. Now, what rent will yield the maximum income? So let's find out what X yields the maximum income. Keeping in mind that X does not represent rent, X represents the number of $5 decreases. So be careful when we do this. So second calc, I'm going to go to maximum. Let's say somewhere in here. I'll just type in 15, somewhere over there. Somewhere in the middle. We'll say 10. Let's give a middle value. So it looks like, oh, that was a good guess. It was 10. So it looks like so there's a relative max of 250,000 at X equals 10. That doesn't tell me the rent. That just means that if I did 10 $5 decreases, my revenue would be $250,000. Well, I want to know the rent per month. Rent per month is 300 minus 5x. So that'd be 300 minus 50. If I plug a 10 in there, that'd be $250 would be my rent. Okay, let's flip this guy over. We got linear functions. This is just kind of some definitions here, so not a lot to fill out at first. Just says that a linear function is a polynomial that has a degree of 1, so x to the first power, and it has this form. where m is the slope, b is the y-intercept. Now note, this is kind of a special little, we typically forget this. Vertical lines are not functions. So technically, when you have like x equals 2, that's not a linear function, technically. A lot of times we just call it that because it's a line, so we call it linear. They failed the vertical line test, so they're not even functions at all. So they can't be linear functions because they're not functions. Then horizontal lines are not technically linear because they're constant functions. Linear functions have an x to the first power in them. If it's a y equals, we'll say 2, that has no x to the first power, so it's not technically linear. It makes a line, but it's not linear. So horizontal and vertical lines are neither linear, neither one of them are linear. Now the average rate of change, and for any function, this is the rule for any function, just the average rate of change. And I think average rate of change would be just overall, like if I was driving to Florida, I would take my total miles driven divided by how many hours it took me to get there, and that's my average rate of change, my average speed. Now, my average speed might have been 50, but I didn't drive 50 the whole way. Sometimes I drove speed limit, 70 on some of those. So let's pretend like we drove 70, and then sometimes I was at a standstill. I was driving 0. So the average rate of change just means overall, what was your average rate? Because the average rate of change in a linear function is constant, because it's a straight line, so its average rate of change is going to be the same everywhere. So we just call it rate of change. We don't call it the average rate of change, it's just the rate of change for linear functions. And that rate of change is slope or m, or rise over run, or change in the x over change in y. Change in y over change in x, or delta y over delta x. Delta means change. So all those things mean the same thing, the exact same thing. Now find an equation for a linear function that meets this criteria. So when I plug in -1, I get 2. When I plug in 3, I get -2. So look at this guy up here. You can call one of these A and one of these B. It doesn't really matter which one's which. We could just call this A, this B. So f of A, we'll do f of B. We'll do this guy first. So f of B, if that's B, would be -2 minus 2 over, and then B minus A would be 3 minus -1. This is literally the same thing as y1 or y2 minus y1 over x2 minus x1. Just the notation is slightly different. This would be -4 over 4, which is a -1. So the average rate of change, or the rate of change, would be, or the slope would be -1 on this guy. So if the slope is -1, again using point slope, so y minus y1 equals m times x minus x1. The slope is -1. Okay, this is my x and y. That's going to be in the final answer, so I'm just going to put those in right now. Now pick an x and a y that go together. So it's totally up to you which one you pick. We'll just go to the first one. So this would be a -1, and that would yield a 2. So if I simplify this guy, -1 and then x plus 1. And if you wanted to put it in slope-intercept form, this would be -x minus 1. So if I added 2, y would equal -x plus 1. So that'd be in slope-intercept form. Technically, this would be fine right here because that's point-slope form. So either one you want to do. The next guy then, and this is the backside. We're flying through this. This error analysis. Okay, so regression analysis. Step 1 is enter and plot the data. We've been doing that. And that's where you enter the data is where you go to stat, edit, put in L1 and L2. Plot the data, make a scatter plot, so that's stat plot. And then check for evidence of linearity. Does it look like it's straight? Find the regression model that fits the problem situation. Sometimes it's linear, sometimes it's curved. Superimpose the graph of the regression model on there and observe the fit. So once you run the regression line, graph them together, and then if it looks like it fits, then use it to make predictions. Okay, so here we go. So use the data to the right to write a linear model for demand in boxes per week as a function of price per box in dollars. So describe the strength and direction of the linear association. So first off, put that data in your calculator. So I went to my list, L1, L2, I put all the data in there. So if you need to pause the video, go ahead and pause it and put that in. Then I'm going to make a scatter plot just to try to describe the strength and direction of the linear association. So let's see if it is linear. If it looks curved, then it's pretty weak linear association. We'll do a stat plot. We'll make sure that this is on. Everything else looks good. I'm going to go zoom number 9 to look at it. Does that look pretty linear? Yeah, it's pretty linear. You could argue that it looks like it has a kind of a negative cubic to it. And we could run the regression for that too. The only way to break the tie would be collect a whole lot more data. So sometimes on the homework and on tests, if you're kind of conflicted, go the easier route. If it looks fairly linear, let's just call it linear. If this is a stats class, we could go crazy with it. But for right now, let's just say that looks pretty linear. So this one, describe the strength and direction. The strength is pretty strong. It's packed pretty tight together. Again, you can argue that there's a curve to it, but we're just going to say it's packed pretty tightly together. And is it the direction then is positive or negative? Well, this one is negative, going down to the right. Okay. And then let's find that, guys. So let's run the regression. So stat calc. I'm going to put this in there. Calc. Okay, so interpret the slope in the y-intercept. Okay, so the slope in the y-intercept. Now this is y equals negative 15358.93x plus 73622.5. So that slope, I'm going to write it out first and I'll explain it here. So this number being negative means for every $1 increase, so every time this increases by $1, so for every 1 unit this increases in price per box, the expected, remember when we're doing this models where it's always expected, the expected number of boxes sold will decrease. That's decrease because it's negative. If it's positive, it would be increase. So it's going to decrease about 15,358 boxes. So every time I raise the price $1, I'm going to lose 15,000 boxes worth of sales. Now, how about the y-intercept here? That y-intercept there, remember y-intercept is when x is 0. So if I made the boxes free, okay, so if the price was 0, so if the price was 0, the expected number of boxes sold, and I put sold in quotes, would be about 73,000. So you got to ask yourself, in this case, is the y-intercept useful? Is it useful? No. That's not a useful piece of information because if it was free, it'd probably be a lot more than that even. People would just take them. So not always is the y-intercept useful. I mean, and the fact that it's beyond the normal domain. The domain of my data was from 240 to 360. So it's not really useful. Use a model to predict the weekly sales if the price dropped to $2 or raised to $4. Again, we say if that's beyond the domain of our data, but it's not too far. So this one's going to be more accurate. It's going to be more useful than saying 0. So I would just plug in, and if you graph this guy, and when you hit trace, just make sure you're on the line. So when I push trace, as I push left and right, I'm following along the dots. That means I'm on the scatter plot. I need to push up or down to get on the line. So now I'm scooting around the line. Now I can type in $2. And you're going to have to zoom out first. So, I'm going to zoom out. And again, when you push trace, right now I see plot up here. That means I'm on the plot. And you push up or down, now I'm on the equation. So hit a 2. It looks like if it was $2, it's going to be 42904.64. And then if I raise the price of $4, that in the screen, it'd be 12186.79 be the price.